Here we have 3 carboys of recently fermented artesian apple cider. The cider comes from apples that have been grown in the Netherlands along the Lower Rhine and the Waal River. This cider was fermented over a 2-month period while the carboys were outside in a process that's called wild fermentation, with the temperatures ranging from 14 down to a low of -2 Celsius. During the process of fermenting, we use a device called a hydrometer, which measures the specific gravity of the apple cider. Here we're looking for the level of sugar to determine whether the fermentation process is completed or not. This can be a very risky process because of infections. In the artesian beer making industry, there's a device called an ice spindle. The ice spindle can measure the specific gravity in beer wort on an hourly basis. This is an open source project based on the ESP8266 processor and a accelerometer as well as a temperature sensor. The way this works is it senses the level of tilt of this particular tube, and from that it can determine the level of specific gravity of the beer wort at that time. I purchased the parts and built an ice spindle to see, will this work for creating apple cider? There are 2 factors with apple cider that could make this very challenging. The first is battery life. This device was built to last for around 2 weeks, which is the normal fermentation cycle for beer. With wild apple cider, the fermentation process usually takes around 3 months. This is mainly because Wi-Fi is very power hungry. The other consideration is related to the Wi-Fi protocol. Wi-Fi works at a relatively high frequency of 2.4 gigahertz. How will that react with a fluid in a carboy or a plastic container or even a stainless steel container that is submerged in water? Will this device be able to access the access point or a local repeater that's either on or next to the carboy? In my case, I had problems with the Wi-Fi because all of these vessels were placed in the back garden far away from the Wi-Fi access point. I only received sporadic readings. This led me to 2 questions. Is there a better protocol than Wi-Fi to use for such an application? Consider the LoRa protocol as an example. LoRa, or long range, operates at the 900 megahertz frequency and works with a stateless protocol. How will it compare to Wi-Fi for this application? In today's episode, we'll examine whether retrofitting such a device with LoRa from Wi-Fi makes any sense. Let's get started. Welcome to today's video. Today we'll be testing Wi-Fi versus LoRa for fermentation use cases. Prior to starting this testing, I did some Google searching looking for any data or testing that's been done of either Wi-Fi or LoRa in scenarios where there was either water or metallic objects involved. Unfortunately, I couldn't find anything that would be useful for either wine or apple cider makers or beer brewers. My rough hypothesis is that LoRa will perform better, and the goal of this testing is to validate that. As you will see, these are very informal tests. Perhaps more formalized tests can follow. We will be performing tests under 4 environmental conditions and 2 distances for both Wi-Fi and LoRa. In total, 16 tests will be performed. The 4 conditions will be as follows. First, our test device will float in water. For the second test, that device will be submerged in 10 centimeters of water. The final 2 test conditions will be done in a metallic container. The first without water, but the second one completely submerged in 10 centimeters of water. Based on the test results, we may do more testing as part of the bonus section of this video. The focus of this testing is mainly for amateurs who brew a low volume of either beer, apple cider, or wine. We've used household items readily available to simulate the fermentation process. In addition, we've built a custom device that sends out 2 random sensor readings. The first is with Wi-Fi, where it attaches to an access point, it sends out an MQTT packet, and then detaches. The second is with LoRa. It sends out a LoRa packet which is received on a LoRaWAN and is forwarded. Let's talk a little bit about the 4 tests that we'll be performing. First, we'll let our device simply float in the water, And in the second test, we'll let the device completely be submerged to the bottom of the water pitcher. The second two tests required a metallic vessel. Unfortunately, we did not have a typical stainless steel fermenter on hand, so we had to get creative. Looking around the kitchen, we decided to use a Ninja Foodie to help us perform this test. The testing again was performed without water and then with water, where the test vial was completely submerged. We also attached and sealed the Ninja pressure cooker top before performing the test. For the infrastructure, we used two different types of access points gateways. Let's start with the Wi-Fi. In this case, we used an Asus AC1900. This is a high-quality consumer-grade Wi-Fi access point. For LoRa, we use the Things Indoor Gateway. This is a simple device that simply plugs into the wall. In Europe, this LoRaWAN gateway costs around 100 euros, while they seem to be available for around $70 in the US. Both of these devices run on the 868 and the 915 megahertz frequencies, respectively. And of course, all of these tests with the Wi-Fi router or the gateway were performed at a distance of 3 and 30 meters from the test device. I've spoken about the test device several times now. Let's talk about how it was built. It needed to be waterproof and work with both Wi-Fi and LoRa, sending out data on both paths. In the end, we settled on using a build similar to the parts as in the iSpindle, including the vial and the Wemos D1 Mini with the ESP8266 Wi-Fi enabled microprocessor. We did not add any sensors as the focus was on wireless connectivity. Instead, we added an RFM LoRa transceiver, which is about the size of a small penny. The cost of this build was around 20 euros. 80% of that cost was for the lithium 18650 battery and the vial. An 8.2 centimeter wire was soldered to the LoRa transceiver, while the D1 Mini already includes an antenna built onto the device. Depending upon the device, we either had to add more pennies or take some out to either allow the vial to float or sink. And finally, an Arduino sketch was written that sends out data on both a Wi-Fi path and a LoRa path about once every 30 seconds. The network topology for this test is a bit complicated, but I hope you will be able to follow. Starting from the bottom, we've already talked about the test device, the Wi-Fi access point, and the LoRa gateway. The access point and the gateway are both attached to the internet. The LoRa gateway connects to the Things Network stack infrastructure. The Things Network is a platform as a service for IoT. We've already registered for a free hobbyist R&D account where the gateway and the test device have been provisioned with the necessary IDs and credentials. We are using the MQTT broker feature of the Things Network stack as well as a public Mosquito MQTT broker. In this case, MQTT is the lingua franca to receive events indicating that a packet of sensor data has been received from the test device. For our simple pass-fail testing, we've also written up a simple Node-RED flow that subscribes to both paths of the test device. When data is received, the Node-RED flow publishes a Tasmoder buzzer command to the Learning Tasmoda PCB device that we created in episodes 1 and 2. We will hear one beep when Wi-Fi traffic is received and two beeps when LoRa traffic is received. I connected Learning Tasmoda PCB to my smartphone Wi-Fi hotspot to ensure that I would receive audible confirmations in all of the tests. This proved to be an ideal topology for this basic testing. With the complete test environment set up, we ran the 16 tests. Before showing you the test results, how do you believe both Wi-Fi and LoRa performed? In which of these tests did both of these wireless technologies pass and fail? Now with a brief drum roll, let's see the results. The test results were not exactly what I was expecting. Of all 16 tests, 12 passed and 4 failed, which I've colored in red. All of the failures were with Wi-Fi and the longer distances when I combined with either water or metallic interference. This is consistent with postings I've read on many beer brewing forums. The Wi-Fi spindle tends to work very well in environments with good Wi-Fi coverage where either plastic or glass fermentation vessels are used. What was surprising is how well the LoRa performed even in environments where both water and metallic interference were present at distances of up to 30 meters. I was especially surprised that the fourth test was successful. What is your experience? Does this testing reflect what you've seen with the iSpindle Wi-Fi performance? Of course, this testing begs the question of the limits of LoRa. Clearly, we've not yet taken it to the edge. So as promised, a bonus test. Let's take the fourth test with the test device submerged in water inside the Ninja pressure cooker. From how far will we receive data readings from the LoRa gateway? With this last test, we will change the LoRaWAN configuration slightly to a more professional setting. Instead of the LoRa Things indoor gateway used at ground level, we will be using a gateway I have placed in the attic of my 3-story home in the Netherlands. I'm using a tall glass 1.4 meter antenna with 8 dBi peak gain and a Raspberry Pi based, actually self-built LoRa gateway. The actual height is at around 8 meters from the ground. When I took the dog for a walk with the test file in my pocket, I could be as far away as 850 meters and still receive data readings. How far do you think we'll reach with this test device submerged in water in the Ninja pressure cooker? From previous testing, we know it will be somewhere between 30 and 850 meters. To perform this final bonus test, we loaded the Ninja pressure in the Radio Flyer. If you're not familiar with the Radio Flyer brand, it's a classic American toy wagon for kids. I looked this up and it turns out that the Radio Flyer is actually now a 100-year-old American company still in business today. The first Radio Flyer was introduced in 1933 at the Chicago World's Fair. The inventor of this toy wagon was fascinated by airplanes and radios, hence he came up with this name. My parents bought this Radio Flyer for the kids nearly 50 years ago, and I still remember it showing up next to the Christmas tree on Christmas morning. This year, the Radio Flyer company evidently released a new red mini Tesla Flyer running on lithium batteries. How times have changed. I digress with that fun trivia. Let's get back to the bonus test. So I went on a road trip with the Ninja in the back of my trusty Radio Flyer, walking through the neighborhood with curious Dutch onlookers wondering what I was up to. How far did I get before I no longer had the double beep confirmation of the LoRa transmission making it back to the gateway? Using a GPS application on my mobile phone, I got short just of 180 meters away, which is around 590 feet. Again, it's really important to think about what we've just done here. This is a worst case situation where we have the measurement device fully submerged in a metallic vessel. Additional tuning of the vial antenna and the LoRa spreading factor settings would have also likely improved the reach, perhaps by as much as 5 to 10%. So, what are the conclusions and what does all of this imply? Well, for sensing, clearly LoRa is a more suitable protocol, especially where minimal data is exchanged. It also requires far less battery life, which is critical for certain types of brewing. LoRa is ideal for longer distances, also where both metal and/or fluid challenges might be a factor. As an example, if you have longer fermentation cycles that require much longer battery life. On the other hand, Wi-Fi is also very suitable, by perhaps being slightly over-engineered. Thousands of ice spindle users can confirm that it's a very suitable technology. It works particularly well for beer brewing, where you have a home with very good Wi-Fi coverage, especially if you're brewing either in a glass carboy of some type or perhaps in a plastic bucket. For the next step in future episodes, we will test a breadboard build of a revised ice spindle device with the LoRa RFM95 transceiver. In order to do this, we will likely need to investigate if we have enough free GPIO pins on the D1 Mini to support both the I2C, the one-wire interface, as well as the SPI pins needed for the LoRa transceiver. My thought was to redesign a new iSpindle PCB and consider having this new wireless feature added to the iSpindle open source firmware project. So that wraps it up for today. Please leave comments if you face challenges with fermenting applications related to Wi-Fi coverage or water or metal interference. I'm especially interested in hearing from any iSpindle beer brewers on this topic. If you found this episode interesting or useful, please like this video. Thanks for joining me on this video, and I hope to have you again on a future episode where we learn, master, and apply. This is Mark at marktroyer.tech signing off.